So the next talk is entitled From Deontic Logic to Mathematical Optimization, a rule formalism for emergency decision making. There we are.
Do you see it?
Yes.
Okay, fine. So thank you for attending. So I've got a few minutes, so I will be a bit quickly about this topic. My topic is about decision modeling for emergency management systems. And we'll start with a rule-based decision problem, which is typical kind of a symbolic reasoning for artificial intelligence, and will transform it into an operation research problem, formulating it as a discrete optimization problem, and will finally brought it to solution using CP technologies. I'm going to answer a question of decision making in case of emergency. In particular, it will be for French fire and rescue services. And when you're faced with an emergency, you have to make quick decision in real time. And the first question we have to solve is, what is the proper plan of action? So this is the tactical decision phase, which is followed by an operational response phase corresponding to its implementation using resources from nearby fire station. But this is a more standard resource allocation problem. So I will focus here on the first question, which is the tactical decision plan. When you've got an emergency call, you've got some information brought to you by the call center, and there are some standards for sharing data about this emergency situation. For instance, you know what has happened, what is the location, what are the risks, if there are health motives, for instance, if there are victims, and so on. So this is a set of information. You will consider it as full information for starting the decision process. And we'll see later on that our decision making is mostly of propositional nature, but not exactly. So that's why I think this way of formulating the problem is of interest. So we'll use a particular kind of rules for knowledge elicitation, which we call gradual decision rules, which are rules of the form the higher A, the higher B, or the more A, the more B. For instance, if you have more victims, you will have more ambulance to send and to dispatch to the scene of the emergency. So because I've got a few minutes, I will focus on a small example for you to better understand the case. So this is a car accident case I imagine for you. It's a rule-based problem as explained in the beginning. So this is the first rule. If you've got a car accident and you've got one victim, then you have to plan a first task, which is a first aid mission. And we'll see in the sequel that our problem is not only of qualitative nature with proposition variables, but also of quantitative nature. If you have more than one victim, if you have several victims, then you will have to plan more than one ambulance. For instance, 2 ambulances with 2 missions. A mission in our vocabulary is a kind of vehicle which is manned. So let's imagine a third rule. If you've got a risk of fire on top of your accident, then you will need to have a fire engine. Fourth rule, if you're on a highway and if this operation has to be set, then you will need some road signal signs. The fifth rule, if you've got a rioting area, this is known to you because you've got a geographic information system, then you will have to plan a commando mission. Other case, if you've got more than 3 missions in your solution, then you will need to have at least 1 commando mission. And the last case for our rule study is if you've got 2 commando missions with a car accident, then you will have a chief on top of that. So you see, the nature of the rules is a very specific kind, and it is a monotonic reasoning. In a way, you push information from left to right following the implication of the rule. It's a purely declarative language, and we are now going to see how we translate it into a mathematical model. So we've got on one side input parameters, and the other side pure decision variables. So I will use y's for Boolean parameters and x's for decision variables. And we use the total number of missions as a derived variable for expressing our problem. So if I want to translate the rule constraint system into constraints, so this is how it looks like. So I've got conditions, Boolean conditions. If I want to use inequalities, it amounts to stating that the Boolean is greater than 1. And the most interesting, most important thing is that our decision variable are set on the right-hand side of the rules. So here we have conclusions on the right-hand side, stating, for instance, that we've got first aid mission, at least one or at least two first aid mission, firefighting mission, at least one in that case, etc. And this is the total number of missions that we plan, which conditions the application of the rule, which is very specific in that case. So it's kind of implicit reasoning in which the conclusion of the rule can be seen in the premises of the rule. So if we want to run this system and query the example to understand how it is activated, I give one example, in which case the input facts are only the car accident. So the car accident, all the rules were concerning car accident, and this is how the system simplifies. Because there are no other Booleans, we assume they are false, so rules 1 to 5 don't apply. There are only rules 6 and 7, but there's no reason why they should apply. In that case, the system is consistent, but no rule applies. So doing nothing is a solution. So we have no mission planned, and this is the optimal solution. Setting of operations in that case would be a waste of resources. So we see we're moving towards an optimization problem in order to solve this decision problem. So I give now a second example in which input facts are a car accident located on a highway and with which there are several victims. In that case, rule 2 applies because there are several victims. So we know that we need at least 2 first aid missions. And also we know that because we're on a highway, if we have already some missions planned, then we'll need to add some more signaling. So first, we derived the fact that first aid mission must be of cardinality 2. And then because this is of cardinality 2, the total sum of missions will be greater than 1. So it will fire rule 4. And as a conclusion, there will be a signaling mission. So the total now of missions will be greater than 2 plus 1, which is 3. And rule 6 will apply, leading to the conclusion that will be a commander mission. And now there's no reason to apply rule 7. So the optimal solution will be with 3 missions, 1 first aid mission, 1 signaling mission, and 1 commander mission. There's no 2 more. So this is a very simple way of solving your problem using constraint translation from rules to constraints and using standard CP resolution. I'm going to explain why it works so far. Here you see the way to dispatch the missions with the commander mission, the signaling mission, and the first aid mission sent to the scene of the emergency. Right. Now, if we want to generalize this tactical response problem, in fact, in order to prove what we want to state about this problem, it's better to view it more generally as minimize an objective function, which is the sum of the missions, because you want to use as little means as possible. So you want to use, this is applying parsimony principle. You've got domain constraint because missions are elementary tasks, so they all denote natural numbers. And all rule constraints or implications of the form if we can generalize it to a system of linear constraints on the left-hand side of the room and a system of linear constraints on the right-hand side of the room, you've seen that the coefficients were very simple. They were mostly 0 or 1. So, but if we can generalize this to a non-negative matrix on the left-hand side and to a monotone matrix, which means a matrix with at most one non-negative coefficients on the right-hand side. And this enables us to prove the property which is of very great importance in that case, and which justify its use as an application in our case, because this modeling has been used as a core component for the French Nexus platform, which develops the new mobilization engine for fire and rescue services in France. So the formulation we had in this slide just generalizes a very standard Horn satisfaction problem. Of course, we move it to generalization. And if you remember, in the Horn case, you've got a least element property. And we find again that least element property due to min-closed properties.
Yes. Sorry,
I'm running short of time. Okay,
Yes.
so that was my last slide. I'm not going to go into the technical details for proving that property. This is a generalization I've shown. I think it's more interesting to understand what's behind it. And it all relies on min-closed problem solving. Thank you very much.
Thank you. One short question, maybe. Could it be that your rule base is unsatisfiable?
Yes, it could be, but it would mean that your policy is inconsistent. Usually, if your policy is consistent, you would expect solutions. So that there should not be the case that it is unsatisfiable. But that means you need to make some checking before.
There is no upper bound of the number of resources.
I don't know. They're all lower bounded. So in that case, yes. Yes.
They are natural numbers, so they are bounded below by 0. That's why if we have a solution, it's an integer solution in that case, and we've got it. And propagation computes it. Propagation does the job. You don't need to do any specific algorithmic design for it. Just reuse propagation.
Thank you again.
Thank you.